So let's explore the idea of the limit of a function by working through a simple little model example here. Suppose we have the function f of x defined by the rule x squared minus 4 divided by x minus 2. Okay? You've worked with plenty of functions of this type over the years. This should not be too surprising to you. We can evaluate this function at a variety of points. Let's consider the point, the x value 2. What is f of 2? Well, when we plug in f of 2, we have 2 squared is 4, minus 4 is 0. 2 minus 2 is 0, and 0 divided by 0 is undefined, right? Division by 0 doesn't work. So f of 2 is undefined. So we know this function is doing something strange at 2. But what specifically? How is it shaped? How does it behave, right? By shape, I mean, the graph. If we were to graph it, what would the graph look like? Or just numerically, how do the numbers behave when x gets really close to 2? Well, there are a few ways we could figure this out. But let's start by trying to compute some numbers, shall we? Let's make a table of x values and f of x values. And we can consider first, we could start nice and easy with some integers, right? So we have 2, so maybe let's try 0 and 1, a couple of points below that, and maybe like 3 and 4, a couple of points above. So suppose x is 0. F of 0 looks like we'll have negative 4 divided by negative 2, and that is positive 2. At x is 1, we have 1 squared is 1, minus 4 is negative 3. 1 minus 2 is negative 1. Negative 3 divided by negative 1 gives us positive 3. Okay. I'll skip a little bit of space here. Hop on up to 3. 3 squared is 9. 9 minus 4 is 5. 3 minus 2 is 1. 5 divided by 1 is 5. And let's look at 4. 4 squared, 16, minus 4 is 12. 4 minus 2 is 2. 12 divided by 2 is 6. All right. Now I skipped some space because I want to start moving in a little bit closer. Right. We have, somewhere in here, we want to know what it does near 2. We know that we can't just put 2 here. We get undefined. So let's move let's kind of pinch in on a little bit. We have 1 and we have 3. So let's consider maybe 2.5 and 1.5. Right, we'll figure those out. Well, 2.5 is slightly easier because there's no negatives. I'm going to talk through the computation in my head. I encourage you to work it out yourself by hand, or maybe use a calculator if necessary. But it's good to practice mental or handwritten arithmetic from time to time to keep sharp on what these things mean. 2.5 squared, well, 25 squared is 625, so 2.5 squared would be 6.25. When we subtract 4, that leaves us with 2.25. 2.5 minus 2 is 0.5, or 1/2. Dividing by 1/2 is the same as multiplying by 2. 2.25 times 2 gives us 4.5. Right? Again, if you didn't follow that, pause the video now, work through it yourself, confirm that that's true. 1.5 squared, well, 15 squared is 225, so 1.5 squared is 2.25. If we subtract 4, that gives us a negative 1.75. 1.5 minus 2 is negative 1/2, so negative 1.75 divided by negative 1/2 will be a positive 3.5. Okay. Now, this is moving in a little bit closer to 2. Let's kind of try to squeeze in closer still. Let's look at 1.9 and 2.1. So you see I'm going, instead of moving up and down 1/2, I'm moving up and down by 0.1, right? Now I'm not about to, I I could do the 19 squared, but that takes more time and effort than it's really worth. You can work that out and confirm for yourself that this will work out to be 3.9. When we do 2.1, we will get 4.1 as a result. Okay. So now looking at these patterns, the sort of the patterns of these numbers, as x gets closer and closer to 2, both from below and from above, smaller values and larger values, we're kind of pinching in on it from both sides, we see that our function values seem to be closing in on 4, right? So it would appear, actually let me go ahead and produce a graph here, which is part of why I don't want to stick the graph. Okay, let's just do it here. And we'll bring it over to about there. Okay, so here's our x-axis. Here is the y-axis on which we will graph the function, y equals, we'll graph the y equals f of x. Let's put, where do I want to put 4? Out there, so let's do like 1, 2, 3, 4, 5, 6, and then horizontally we have 1, 2, 3, 4. These are just approximate. So let's graph some of these things. We have 0, 2, that's that point there. We got 1, 3, so that's there. We have 1.5, 3.5, that would be right about there, give or take. We have 1.9, 3.9, something like that. 4, we have 6, around here, I'm just sort of eyeballing this. At 3, we had 5. F of 3 gave us 5, that's about there. 2.5, we get 4.5, so here's 2.5, 4.5. 2.1, 4.1. You see what's happening here? These numbers seem to really be closing in on this spot right here. When x equals 2, the function is undefined. But when x gets very close to 2, the function seems to get very close to 4, right? The function value. And I've only plotted a few points here, but if you plot more points, you will find that indeed we can connect these with a straight line going this way and that way. This function f of x is defined for all real numbers except 2. It is not defined at 2. And if we graph it accurately, we get a small little gap at 2, but otherwise it's a straight line. Okay, so there are a few ways we can describe this behavior. Using some of the language that you might have seen in a previous class, particularly when talking about end behavior of functions, we can say something like, as x approaches 2, f of x approaches 4. This rightward arrow in this in the context of calculus, we usually read either as approaches, or more informally we sometimes say goes to, as x goes to 2. But that's, it's kind of it's a bad verbal habit that I have. I'll try to stick to approaches. That is more accurate and a bit clearer. As x approaches 2, f of x approaches 4. Or, grammatically, an equivalent way to say this is that f of x approaches 4 as x approaches 2. Now this is a little bit cumbersome, so we create a special notation for this. We describe this idea of approaching as a limit. What is the limit of our function as x gets close to a particular thing? So this sort of situation we would describe symbolically and somewhat more compactly with an operator that we call, we write it as lim, we pronounce it as limit. Below this symbol, or as a subscript in text, we will describe what our independent variable is doing. In this case, we're looking at what happens as x approaches 2. So we'll tuck a little x approaches 2 underneath this limit symbol. And this together means that we're going to investigate whatever expression follows, right? And we're going to see what it does as x approaches 2. In this case, the expression in question is f of x. So I can just write f of x. If we didn't have a name here, I could have just written out the symbols. You know, you can write out an expression like x squared minus 4 over x minus 2, whatever. This limit just means whatever is after it, whatever term follows, we're going to figure out what it's doing as this variable approaches this value. So this can be read somewhat formally as the limit of f of x as x approaches 2 equals 4. If a limit exists, we would say that it has a value that is whatever the function is approaching. Now, this is important. We're not saying that f of x equals 4. Looking at this graph here, we see that actually f of x never equals 4, does it? What we are saying is that as x approaches 2, f of x approaches 4. So this thing we call a limit, we're defining to have the value 4 in this case. Okay. Now, whether a limit exists is somewhat independent of the question of whether a particular whether a particular function value exists, right? So f of 2 is undefined. F of 1 is not undefined, right? F of 1 equals 3. We know that. We see here 1, 3. We computed the 1, 3 here. F of 1 equals 3. This fact does not automatically mean that the limit as x approaches 1 of f of x is equal to 3. Just knowing the value of f of 1 does not tell us what the limit is. The limit is asking what happens as x takes on values that are very close to 1. Okay, so we have to consider what else is going on there, right? So in this case, we would either do some numerical work or consider the graph. If you plug in some numbers, some values of x that are very close to 1, you should find function values getting close to 3. Looking at the graph here, when we look at when x is near 1, looking at just this little neighborhood around here, and see what kind of function values we get. Well, we look and we see, oh, well, the function values, all of those function values are grouped together really close near 3, right? So with a numerical or graphical analysis here, we can see that this limit actually is equal to 3. But it's important that this is not because f of 1 equals 3, it's because of what f of other numbers near 1 is equal to. That's how we go at these things. The function value could be completely different, right? I could define this function in a piecewise fashion. Maybe f of x is equal to this when x is not equal to 2, and then when x is equal to 2, I could say, oh, well, then f of x equals 5. Well, then its graph would have this isolated point separated from the rest of it, and f of 2 would equal 5, but that would not change the fact that the limit of f of x as x approaches 2 is equal to 4. When evaluating limits, sometimes it's useful to consider what the function itself is doing. We'll talk in later sections about what it means for a function to be continuous, and knowing something about its behavior. Sometimes evaluating a function at the value in question can give us the limit under certain circumstances. But we have to know something about the function in order to expect that to be the case. Okay? In general, the value of a function at a particular value of x and the limit of a function as x approaches that value could be entirely different and unconnected, basically. Okay? So a sufficiently accurate graph will help us see such issues, The problem is with getting a sufficiently accurate graph. Many of you are probably accustomed to, if you want an accurate graph, you turn to a graphing calculator or a computer and you ask it to graph your function. The problem with that is with how these things actually graph functions. So if you ask a graphing calculator to graph a function, what it does internally, it's not smart enough to do the things that humans do where we say, oh, this is a linear function, this is the intercept and this is the slope, so I'll just draw a straight line. That's not how any of these operate. It graphs a function sort of like what we did here, where it creates a table of it creates a table internally. Well, it doesn't literally build a table, but it does this idea of moving through x values, one after the other. For each x value, it plots a corresponding, it evaluates what the function value is, so that gives it a pair, and it plots a point. Actually, let me kind of sketch a rough little picture here. If we have a standard like, suppose you have your standard like -10 to 10 viewing window that shows up in a lot of like your standard graphing calculators, for instance. The calculator will take your viewing window, whatever your range of x values is, and it knows how many pixels are on the screen, and it divides the range of x values by the number of pixels to find out how much x increases at each step. And it starts at the left pixel, and it says, okay, well, what x value is this? It's -10. It'll check the function. Okay, what value does the function have there? Okay, maybe it has this y value. All right, fine. And then it moves to the next pixel. And it says, okay, what x value corresponds to this? Now, most of these screens have widths that are like 72 pixels, 96 pixels, that kind of thing. So if you're going from -10 to 10, and you divide by the number of pixels, you get some weird decimal result. You've probably noticed if you ever used the trace feature on your calculator, and you just arrow left and right, your x values it shows are usually these big messy decimals, right? They aren't usually clean. So it gets this decimal value, and it computes, and maybe it finds, okay, well, maybe at this x value, the y value has come up to here. So it plots that point and connects them with a line. I mean, it doesn't plot the point and then connect. I mean, but it draws, it knows, it holds on to what are the coordinates of this point, what are the coordinates of that point, and it, fills in the pixels from this one to that one to create a little line segment. And then it moves to the next pixel. It says, okay, what value of x is this? Let's compute the y value. We get an xy pair, that's maybe this point here, and it connects those. You can kind of play around with this if you change the, if you go into your window settings in a graphing calculator and change, it might be called like an x step or a delta x or something like that. And it usually defaults to 1 or 2, but if you make it a larger number, 3, 4, 5, and you graph a curve, like a polynomial, maybe a parabola, for instance, you will note, if you make this large enough, you will note that it, rather than looking more like a curve, it'll look kind of chunky, like it's connecting, you can see that it's connecting line segments. It only looks relatively smooth because it usually puts these so close together, and the pixels are large enough anyway that, well, they're actually kind of chunky when you look at them. These aren't really straight lines. So it kind of just connects all of these things to piece them together. Now, this is important to understand because it explains why, if you graph this function in a calculator, a normal graphing calculator with the default zoom, it's usually option 6 on the Texas Instruments calculators, zoom standard, it will produce a straight line with no gaps. It will just look like a solid straight line. And you might look at this and say, oh, okay, fine, 2, 4, no big deal. There are no gaps, no problems, nothing. But the reason that it would look that way is those crazy x values it gets when it divides it. It will evaluate x values before 2, one by one, and it plots points as we go. One of those x values will be just a little bit less than 2, and it'll plot that point. And then the next x value, it will probably hop over 2 and plot the next point and connect them with a line. It doesn't even know there's a gap in between because it never actually evaluates f of 2. It evaluates f of like 1.97 blah blah blah, some random string, and then it happens to go to f of 2.04 blah blah blah. I'm just making up numbers, but you get the idea. Like it's just sampling at values, and it will usually hop over those. There are a couple of ways that you can check these sorts of things with your calculator. One of them, if instead of just using trace, you go into the, well, there are two ways to do it. One of them is to, when you go into the calc menu, I don't remember what it's called. It might be called value. You can go through that, and it'll ask you for a place to evaluate it, and you can type in 2 and enter, and it would say undefined, or just leave it blank. Or another thing you can do if you do use trace, many of you are aware of this, but some of you probably are not. When you get that little cursor and you're using the left and right arrows to trace along a function, you can just start typing a number, and you'll see that you're typing into the x value. So if you hit trace and it pops up a little blinking cursor right here, for instance, you can just type 2 enter, and it will jump. Well, if you type 1 enter, it'll jump right to this point. If you type 1.5 enter, it'll jump to this point. If you type 2 and enter, it'll either say undefined or it'll just have a blank, depending on what calculator you have. So you can force it to test that. Another thing you can do, I mentioned that part of the problem was the particular, the fact that this is going from -10 to 10, and that range of 20 in the x direction is not an even multiple of the number of pixels. Like they don't divide out evenly. And that is an issue with what's usually called Z standard. But there is another zoom in your zoom menu. If you look at Z decimal, Z decimal is usually defined in such a way that each pixel represents a step size of exactly 0.1. So it'll go up to, it's not going to end at 10, it's going to end at some number depending on how many pixels wide your screen is. Goes left and right. But it samples at intervals of 0.1, which means in particular it's sampling at integers and the tenths of the integers, but it does hit all of the integers. And if you graph the function f of x with zoom decimal, you will see in the graph, you will have this line, and then if you look carefully, there'll be a tiny little gap in the line. Just 1 pixel missing, because when it tries to graph 2, it's undefined. So it doesn't plot a point, it doesn't connect it to the points before and after. You get this, you'll get this discontinuity there. So that's a way, if you're trying to examine, if you're trying to look at what a function does and you suspect that there's a problem either at an integer or at a tenth of an integer, then Z decimal will take care of things for you. Now, if the problem is someplace else, like, maybe it's at 1/3, for instance, well, that's not going to fix the problem because it'll still pop over that, it'll still just kind of jump over that gap and not realize there's an issue. And that, that's why we need to think about these things, do some analysis, figure out domains of functions. The calculator itself is not going to, will very frequently not show us where there's an answer, where there's a problem unless we tell it to. And it's not just a problem with the TI-80 series calculators. If you go to, I don't know if you've done this, but if you go to Google, for instance, and you just type into the search box the word graph followed by a space and y equals and some definition. So in this case, it would be like x caret 2 minus 4 in parentheses. I'm running out of space there, but then, divided by x, so minus 2. Is that what I was doing? Yeah. And you hit enter or click the search button. It will, above some search results that aren't going to mean a whole lot, it will have a nice graph for you. Like it's going to have a little widget that, it shows you, it'll show you like a graph of the function, and you'll see a nice blue line, and it's nice and smooth, looks way better than Graphing Calculator. As you move your cursor around there, it'll show you like the coordinates. You have various options for zoom. So like if you're on like a desktop or laptop or something, you can use like your mouse scroll wheel to zoom in and out like you would expect. You can just point your cursor at a point and zoom in or zoom out. If you're on a device with a touch screen, like a phone or a tablet, you can use you can use the 2-finger motions to. Do you need 2-finger to? I mean, to zoom certainly. I'm just thinking about it in terms of panning. I think you can just use the 1 finger and drag the thing around like you would normally. You can just grab it and drag it around to kind of pan around the view. Same thing with a mouse. You can just click and drag to move it around. But for zooming, you can zoom in and out with the scroll wheel, or you can use the the pinching or expanding with the 2-finger gestures to zoom in and out on a device with a touchscreen. It is extremely slick. For simple functions that don't require terribly advanced things, I use Google to graph lots of things because the graph is so easy to work with. However, if you graph this function, you'll just get this nice smooth line, and there's no indication of any problem at all. And if you point at 2, 4, and you start zooming in with your scroll wheel, and it takes a little bit of time because you have to zoom in a lot, and you have to keep kind of adjusting the cursor to get close to that point so it doesn't stray off the screen. If you zoom in and zoom in and zoom in, so that the values start looking like 1.9999 to the left, and you get like a 2.00001 to the right. Like, I'm just making up numbers, but I guess there would be another 9. Somewhere in this vicinity, you will start to notice a weird sort of little wiggling. And if you continue to zoom in, you start getting some extremely erratic behavior. And that has to do with the limitations of the standards for floating point computation. Calculators and computers fundamentally have problems with very, very tiny differences. I mentioned this in my notes, but it's important, so I'll mention it here in the video as well. The textbook has a document called something like Lies My Computer and Calculator Told Me, or maybe it's Calculator and Computer, whichever. And this used to be an appendix, but it's no longer in the physical textbook, but they host it on their webpage. And it is a very useful thing to be aware of. You can enter something completely correctly into your calculator, and it can give you catastrophically incorrect results. And if you don't know how the internal representations of these numbers works, like how it does these things, you might never suspect that such a thing would happen. So, it is important to, graphs are very useful to get rough ideas of things, but just using a calculator or a computer with no analysis does not necessarily give you a complete or accurate picture. Something else that can help, there's something calculators are really good at, and that is automating repetitive actions. So, for instance, if you have something like this, and you are asked to numerically explore this function to find its limit as x approaches 2, that means that you need to evaluate this function at x values to get closer and closer to 2, and record them and see what they do. Now, what many students will do is take their calculator, and you might take something like, okay, let's suppose x is 1, and you can type in 1 squared minus 4 divided by 1 minus 2, use appropriate parentheses, hit enter, you get, in this case, 3, you can write that down. And then you take another value like 1.5, and 1.5 squared minus 4, and you just keep repeatedly typing these things, but that takes forever, right? That is not fun. Nobody wants to do that. So, like I say, calculators are very good at automating tasks. One thing you can do to save a lot of time, those of you who've done a lot of graphing of functions and are very comfortable with your graphing calculators are aware that, oh, you can just put this into the y equals screen, call it y1 or something, put that into y equals to graph the function, and then you can do what I was talking about, where you could do like, you could hit trace and then type the number you want and hit enter. That's a whole lot faster. So you could hit trace 1, enter, and write down what y value it gives you. And you can hit trace 1.5, enter, and then write down the y value it gives you, and so on. There's another very useful feature of these graphing calculators, and that is table. If you put the function into y equals, just like you would graph it, so you have a function all ready to graph, maybe you even did graph it, doesn't matter if you actually graph it or not, and you go into table, by default what you'll usually see is you'll see something like x and y1 and some kind of thing like this, and there'll be a whole bunch of numbers listed down here and the corresponding y values. If you go into table set, which is usually a second feature on table if memory serves. It's been a long time since I used the 80 series calculators, but I believe it's something like that. Poke around depending on which calculator you have, right? So if you have a TI Nspire, a lot of these things will be very similar, but some of them will be slightly different. You might need to check your manual. But if you go into your table settings, you'll see something like, you'll have like some sort of a delta x, or like I said, an x step, something like that. And that will be, so there'll be a setting for what your first x value is, and there'll be a setting for the step size. So for example, if it starts at like, for example, I don't know where it starts, but if it starts at 0 and then goes 1, 2, 3, and on down the line, then your delta x or x step in that case would be 1. It's saying that you increase by increments of 1. If you wanted to only find even values, you could change that to 2. If you wanted decimal values, going from like, 0.1, 0.2, 0.3, and so on, you could turn the step size into 0.1. But what's really interesting for our purposes here is that somewhere in here, there is a setting where you can switch between two modes. There is an auto mode and an ask mode. There's something at the back of my brain that tells me that some models of calculator might actually tuck this into the mode button instead of the table set feature, which would be terrible, but that might be the case for some of you. You might have to poke around with your calculator and see where it is. But either in table set or in the calculator's general mode settings, there is an option to switch between auto and ask. And it usually defaults to auto. But if you switch it over to ask, then when you go into the table, you see none of this, you just see a blank. And you can use arrow keys as necessary to move around. This first cell is probably highlighted. And what you do is you just type an x value and hit enter, and it gives you the corresponding y value and moves the cursor down to the next line. So you might see where I'm going with this. You can type this function as your y1 in your y equals screen. And then you can make sure that your table is set for ask. Go into table and just start typing things like 0, enter, 1, enter, 1.5, enter, 1.9, enter, 1.99, enter, 1.999, enter. You can take as many ditches as you want and see what it's doing. And then maybe you shift gears and go, okay, let's go like 3, enter, 2.5, enter, 2.1, 2.01, 2.001, 2.0001. Like, you can just move on down the line, typing in whatever you want. And unfortunately, I don't have any mechanism by which I can record those. It occurs to me as I'm saying this, it'd be really nice if I could just show you. The same thing happens in class when I give this lecture in person, though. I just sort of write these things on the board and say, try this out later on your calculator. If you have any questions about that, let me know. But I do recommend that you experiment with that. It can make a lot of these numerical and graphical questions, when we're trying to numerically estimate limits, those types of options can be extremely convenient and really speed things up. So, I mean, there you can see, like, I know so far, there have been several times I've talked about how, we can't trust our calculators and all of these sorts of things, but I genuinely do love calculators and computers. They are extremely useful. They do a whole lot of things for us. If you know how to use them right, they can speed up your analysis tremendously. They're fantastic. But they do have very, very strong limitations that a lot of people are unaware of, and it's important that you know what those limitations are. And getting around those limitations requires understanding the functions. So the calculators do not replace our rigorous pencil and paper analysis. We still have to be able to think through these functions, understand, okay, what's the domain of this function? How does this behave? What's going to happen when we do this? And, we can use things like calculators and computers as auxiliary tools to speed up the grunt work, basically. But yeah, hopefully that cleared up or illustrated at least something with how limits of functions work and some of the both theoretical and practical considerations involved in evaluating these.